you will find that before the Bannock, there was no such conditions. Okay, you see the Brouwer, there is no such condition. Brouwer is very simple, simplest I can say that theorem, that you have the fixed point, that you have a continuous function from a closed interval to the closed interval, and this continuous function is have a fixed point. Okay, they are not talking about the uniqueness. That's the difference only. So Bannock has given the uniqueness, but if you look into the hypothesis of the Bannock, you will find that that way Bannock is a very strong hypothesis, strong results, lot of. Its own contraction is loaded, or I can say that inbuilt continuity. It's a strong. Apart from that, one inequality, again a strong. After that, providing the uniqueness, means just for the sake of the uniqueness, lot of hypotheses assumed for this theorem. And after that, you see everyone is running behind the contractions. And like the Chirik's contraction, the maximum possible combinations, that was taken care. Okay. So now the professor is going to speak on this. This is over, sir. Contraction part is completed.
Just 5 minutes.
5 minutes. Okay. Okay. So after I think a few more information he has to pass you people. So after that he will talk about the multi-valued mapping, right? Multi-valued mapping, no? Yes, multi-valued mapping, and it's a fixed points. So as I said, single valued, multi-valued, set valued. They are all looks alike, but they are all different. So I think definitely you are going to talk such things. So he will speak about this also. Make a distinction of all such things. Wherever needed, you go to the room and home and do some homework. Okay. And may I ask you, how many of you are interested after 5:30 for a interaction? Please raise your hand. If you are interested, then only I will request my colleagues to stay over here. Otherwise, their work is also very hectic. So, how many of you wants to stay? Because anyway, we have an open session, 2 hour session, maybe on Thursday. I think it will fall in Thursday. Any one of you? No. Okay. No issue. So, yeah, maybe because some heavy classes. So, I request Professor V. Mani to continue his lecture, and this will last till 5:30. In between, I finish some of my work and back to you people. Okay? Thank you. Okay, Professor?
Yeah, thanks, Professor Murthy. Okay. So, sir, before any doubt in whatever we discussed yesterday, today, till now? Any doubt? So, that's why you are not asking doubt, so I will give some more homework as Professor Murthy suggested. Yeah.
In precisely merits of this contract, cyclic contract.
Merit of?
Cyclic contract.
Merit is?
In precisely way.
Yeah. The cyclic contraction, when there is no fixed point. That's it. Later this again tomorrow we'll talk. We have two non-empty. See, it's like this. One, this wall is a plane. Opposite side is another wall. All one, that's it, either this wall or two disjoint sets. This is A, this is B. Elements in A, even this is enough. Instead of T from A to B, need not be cyclic even. If some cases we can assume T of A subset of B, T of B subset of T of A. In fact, originally we started this work in 1997 with my student Sadiq Basa. Later he also has done lot of work in this area, ACTA, science, math, Seagate. And then 2000 Journal of, again with both with my student, Journal of Approximation Theory. That time we are considering A and B to non-empty sets. T is a map from A to B. Then under what condition one can find an X in A, there exists X in A such that X in A means Tx is in B, such that distance between the point X and Tx, among all the points, Tx is the nearest point to B. That is, this is less than or equal to distance between A comma B for all small a in capital A, B in capital B. This is what our aim. To achieve this, we are trying to find a point X in A, so the distance between X and A equal to distance between A comma B. If this so, this is less than or equal to distance between A comma B for all A, because this is nothing but infimum or greatest lower bound of distance between A comma B, A in A, B in B. So we give sufficient condition, under what condition we can find an element X in A such that distance between the point X and Tx equal to distance between the set A comma B, that is the minimum distance. In particular, for closed set suitable condition A and B equal to 0, that case we will get distance between X equal to Tx also. It will include fixed point, but more generally if there is no fixed point, what is the next best thing? That is why we have two vertical lines. Then we find a point X, the Tx, that is the nearest. See, for example, this. We give the vertical distance, we will give other type also. See here 0, 0, 0, 1, 1, 0, 1, 1, vertical line. If we take a point here 0 comma x, that goes to 1 minus 1 comma 1 minus x. So like that. So similarly we can even A to B alone, let us say. Similarly if you want to, we can define B to A. This is clear? Vertical line. A equal to the vertical line joining 0, 0 and 0, 1. Capital B, vertical line joining 1, 0 and 1, 1. Map is this way. 0 comma x goes to, because it should be in B, x coordinate 1, y coordinate is 1 minus x. Which is the best, nearest, see you want application you want to see. All the people from A move to B. Some person I want to go, which is the nearest among all. Who will get, you want, can there exists a point X in the domain A, such that the corresponding, the new name for X is Tx. So the distance between X and Tx is minimum among all the distance between A comma B. So which point will we work here? We can see geometrically. What is the distance between first A comma B? Usual metric. See, distance between A comma B means if you take a point here, you have to find all the, one point here, then you have to take the infimum. What is the infimum? Pardon? 1. So which point in A, distance between that point 0 comma x and T of 1 comma, 0 comma x and 1 comma 1 minus x equal to half 1 by 2. So there exists a point 0 comma half whose image is again 1 comma 1 minus x, again half, 1 minus half, that is this midpoint. So we get this point, the mid, this is the nearest. So that is our motivation. So there are under what condition? Later this that's what we, even that whatever we call cyclic contraction, that we introduced in 2006, which appeared in Journal of Mathematical Analysis and Application. In fact, earlier that we will discuss non-expansive map jointly with Anthony Eldred, myself and Professor Kirk.
But sir, that paper is not available online.
Which paper?
You say Kirk and you.
Kirk and me, that paper. Cyclic or?
Cyclic contract.
Oh, that is maybe that Cluj-Napoca or that journal of, maybe we have to ask Professor Merende from their university. In fact, that we were discussing, informally, we were discussing some other things related to best proximity.
That paper have a good number of citations.
Yeah,
The paper is not.
that is very simple. That is many that's the main thing is the second version that we appeared in 2006. Yeah. Yeah. Okay. If you have thing, if you send, I don't have this, I don't know now I will have this because I don't have, now use only cell phone on email, but I can ask my student or somebody who can send it. Okay. So any doubt about, okay. We will discuss related things in the, tomorrow we will discuss about, now one lecture mainly meant for best proximity points, that time we will discuss in detail. Okay, before that, some contraction, some very simple exercise, only you have to use triangle inequality suitably. X complete metric space or metric space doesn't matter. T from x to x, 0 less than or equal to k less than 1, first condition, distance between Tx, Ty less than or equal to k time, distance between xy for all xy in x we know. Now this implies, prove that there exists alpha greater than 0 such that distance between Tx, Ty less than or equal to alpha time, see alpha strictly greater than 0, we are not telling less than 1 or anything, such that distance between x comma Tx plus distance between y comma Ty for all x in A, y in B. This is very trivial. Okay, suppose only this condition is satisfied. T is a map from a metric space X to a metric space, no completeness, nothing. Such that for some alpha positive, distance between Tx and Ty less than or equal to alpha time distance between x comma Tx plus distance between y comma Ty. Suppose it has a fixed point. We do not know whether it has a fixed point or not. Suppose it has a fixed point. What can you say about that? Can there exist more than one fixed point? Under this condition. Can there exist more than one fixed point? Proved by contradiction, or what will happen if Tx equal to x and Ty equal to y? Suppose Tx equal to x for some xy in x, Tx equal to Ty, you write it. What will happen? This condition is satisfied. Tx is a fixed point, means this is 0. This is 0. That means distance between Tx and Ty 0. Tx is Ty. Huh? Why? Tx equal to Ty.
X and Y are equal, there is only one fixed.
Tx,
Unique, only one.
x equal to Tx 0, y equal to Ty 0, this is 0, Tx equal to Ty, will it imply x equal to y? When it will happen? Or it is?
So 1, 2, 1.
Pardon? If it is 1, 1, it is okay. If it is 1, 1, then that case this T in Tx, Ty. For what xy? Whether you have to put some, suppose this is true for any xy, correct? We have put any restriction on x and y? No. Suppose let us fix one x, say x naught. Fix x equal to x naught. Fix x equal to x naught. Okay, then what happened? Distance between Tx and instead of y equal to, okay, x, we will call it O, okay. Fix x naught equal to y. Then distance between Tx and Tx naught is 0. If this between Tx and Tx naught is 0, but what we have assumed already, we forgot something, x and y are, even we don't require this. This we are, what we are assuming that x and y are fixed points. So fixed point means x equal to Tx, y equal to Ty. Hence don't go for distance between Tx, Ty equal to 0, but because Tx equal to x, Ty equal to y, distance between xy is 0. That means x equal to y. Okay. So this condition will imply Tx equal to x, Ty equal to y, imply x equal to y. If they are, then it will become unique fixed point, whatever may be the, it may be a contraction map or Chatterjee or some other map including non-expansive. Suppose T from K to K a non-expansive map, under some condition it has a fixed point, in addition to that it satisfies this condition, then also it will give you a unique fixed point. That's what if you observe that exercise, contraction case also you will get this. Same thing, second exercise, many things, distance between Tx dy less than or equal to k time distance between x and Tx plus y and Ty means that is Kannan map, that alpha equal to k, but go to x comma, as I discussed, y comma Tx for all xy in x. Then this also, suppose this imply, again this imply the x is alpha greater than 0, such that distance between Tx, Ty less than or equal to alpha time distance between x Tx plus df, just use the triangle inequality. So do simple exercise, okay. That's it. If it is contraction also we will get this condition. Kannan map already there, even it is Chatterjee. So most of the uniqueness this will be, alpha need not be 1 or anything, alpha is just any positive number, okay. Any other thing you want? Any other doubt or anything? Now we will move to, essentially we are going to make it light, it's already late, no? So we'll just a game. No need of any knowledge of anything, set theory. Only set theory, some inequality, less than or equal to we know. Only that much. Then from there we will come to what is called Nash equilibrium point. We will not define Nash equilibrium point. From there what we are going to get is called Nash equilibrium point. Okay. So this you can do as an exercise, we will come back. So now let's study a game. I mean, more generally we can have n person, even the cyclic, what we started with 2, in fact it is Professor Kerr going to start with 2, we go for n. So he started with A1, A2, then A3 like that. Idea is T of A1 subset of A2, T of A2 subset of A3, T of An minus 1 subset of An, that is started one. So like that. Then under some condition we will find some distance between, under suitable condition, distance between A1 and A2 equal to distance between A2 A3 like that. So but interesting thing, even 2 is A to B, find a point x. So the distance between x and tx is the minimum. That is, we call it best proximity point. Okay. Now we have, let us start with, instead of n players, see, player need not be playing cards or playing some game, gambling. It may be 2 manufacturing business people. So they have an understanding. Okay. So we have a player 1, we can call it F1, F2 or capital M set of rules for player 1. In a, they call it, it is a strategy set. That means the first player can select any one element from his strategy set. That means they are manufacturing, say, washing machine. They will announce this many washing machine I am going to manufacture. He will inform the other unit. 2 player, first player will inform the other player, I have selected X. Then you select a strategy Y, so that you will get maximum. Both are understanding. Not that I get the maximum, you get the minimum or loss. So we want to find a situation where both player will get the maximum profit. So under what condition we can achieve that? So we don't going to assume anything, just it is a set n m strategy or set of rules, I will write set of rules for player 1, n set of rules for player 2. So we have m cross n. What is the natural? See, after manufacturing, first thing, the manufacturing is not a natural number in our case. It can be a non-empty set. We will see under. So the first player has selected a strategy, say X. We will not say 1, 2 now here, a strategy X. First player selected a strategy X from M. Then he has informed the player 2. Now I have selected, I have manufactured this many unit. Now you manufacture, that means I have manufactured X unit. I am going to, this will go to market and they will decide where it goes. Now you select in such a way that you get the maximum profit. Then that case, if the player select X from M, second player select Y from N, then both will get some income. Income may be positive or negative or zero. Okay, that we call it. So, in a natural way, we have a function f from M N to R. This is called payoff function. Payoff function for player 1. And G from M cross N to R, that is called function for player 2. This is clear? See, in general it may be, if necessary, we can restrict the codomain also, that is different. Right now we allow them R, some real. What is the meaning of this? What do you mean by f of xy? What is the meaning of g of xy? What is the meaning of first f of xy? If we select first player has selected x from his strategy set, he cannot take anything different from outside, he cannot go. He has to take x from M at a time x, one element. He has selected x and inform the second player, I have selected x. Now you select any other y, take anything which will give maximum profit. So what f of xy at a time, that will not decide the maximum. That is if the first player select x, second player select y, f of xy is the income for player 1. G of xy is income for player 2. If it is loss, many times in game thing, instead of profit they will go for loss, minimize the loss. You want maximum or minimum? Your choice. You want to maximize the profit or minimize the loss? Pardon? Minimize the loss, very good. Okay, we want to minimize the loss. That means what? So that is, so what first player has selected x, then the second player, he can select any one strategy from where he can take from his strategy set N, such that if he select this y, x already he has fixed first player, then his profit should be minimum. Loss is minimum. That means what? This is for second player. You are talking about second player loss or this. That means G, first player already selected x. If it is maximum profit, means this criterion are equal to this. Loss should be minimum, so less than or equal to, correct? F of x comma y, then it is correct. That means the second player have not, how do you know? That select some y which we do not know. See, among all, see, let us say m equal to, symbol came, toss a coin, 0, 1. chess mean okay, whatever the thing, or rolling a die.